Okay, hello everyone. So as was just mentioned, we're working on a standalone vacuum test station for Lockheed Martin Silicon. I'm the team lead, Garrett Sempel.
I'm Carl Morlock.
I'm Patrick McGraw.
And I'm Paul Coble. As far as our company overview is concerned, Lockheed Martin Silicon is a subdivision of the well-known defense contractor Lockheed Martin. In specific, they focus on underwater systems. All their products are weapons grade. They focus on electronic warfare products, military communication systems, and sensing probes. A sensing probe is actually what put Sipkin on the map. They made the expendable bathythermograph, which is a water sensor, and it's what actually made Lockheed purchase them.
So we were tasked with developing a standalone vacuum test system for Lockheed Martin. The system had to be able to pull a vacuum on five external units under tests, effectively turn them into their own little vacuum chambers. They had to hold the vacuum for the entirety of the test duration and measure any differential pressure loss. We also had to develop maintenance documentation, a software interface that was capable of communicating with Lockheed Martin's LabVIEW front end, as well as quality control and calibration points.
During the initial steps of the project, we first began by hitting the ground running and doing initial research on vacuum systems, everything from various pumps and designs to testing methods and everything in between. Once we got a good foundation of knowledge, we then started developing various pneumatic systems and performing trade studies on all of them. The first pneumatic system used a pre-charge tank. This pre-charge tank would decrease the time that it would take to create a vacuum in each unit. However, it was determined to be not necessary and also a potential hazard, as well as creating potential wear and tear on the product due to the rapid pressure change. The second design was able to test 5 units under test. However, it was complicated by excess components, such as flow meters and check valves that were determined to not be necessary and could be eliminated through our testing procedures. The third design that was chosen based on its simplicity and durability, which you can see a little preview of it in the upper corner over there. We also began our initial control system analysis, and I will hand that off to Paul right now.
Before beginning our system level design, we started by selecting components for the pneumatic system, and all our components were selected via trade studies, which weighted our possible components over a variety of parameters such as maintainability and replaceability, which were the two most important to our client. After that was done, we worked over towards finalizing the control system and how the basic operation of the control system would work. You can see the original block diagram for that is on the right side of your screen. And following this, we just tried to generate our timeline for the second semester so we could remain on track. And the timeline reflected that we needed to get things done earlier to get them through export control. Following the system level design, we worked on our more detailed design. This portion of the project involved a significant hiccup. We chose a 2-2 solenoid valves, which they seal off the units under test in our system. And the one that we chose had a 4-week lead time. Lockheed wanted all their components to have a 2-week lead time. So they came back to us right before our winter break with their selection for the 2-2 valve. Unfortunately, their selection was 24 volts, and the electrical system we had designed was for a 12-volt 2-2 valve. So this required a total redesign of the electrical system, from the relays, relay driving chips, and the power supply. Everything involved except for the microcontroller needed to be redesigned. Following that, we worked towards our testing procedure. We generated protocols for a power-on self-test, which ensures that all the major components, the transducers, are connected to the system when the system powers on. If not, it will tell you which ports failed or that the whole system failed the post-test, and then it will hang in operation waiting for you to check the connections. We also made a validation procedure, which just validates the functionality of all the UUT ports and that they can be used for testing.
We divided our validation into 3 separate groupings. We had the validation of subassemblies, the actual validation of procedure, which is used in their facility, and the actual operational procedure. Within the subassembly process, we tested 3 separate subassemblies: the relay driving subassembly, which makes sure that our microcontroller, relay driver chips, and relays are all communicating appropriately. The solenoid subassembly, which is basically tacking our solenoids onto the end of that relay driver assembly to make sure that they're all operating as intended, we can actually control our solenoids. And then the microcontroller test, which verifies that the microcontroller, analog to digital converters, and the solenoid, transducers can all communicate appropriately. We were only able to perform half of the transducer test though, because our transducers have not yet arrived. Our second test was our validation procedure, which is going to be used in Lockheed's facility every once in a while to make sure that our system is operating as intended. This involves a full system test, checking that every gating system works, that all the components on their own are working, and just that the system is operational. The final full operational test is the actual procedure the system is supposed to be running in their facility. That's an export control process, so we can't fully describe it, but basically we're pulling a vacuum on the attached units under test, waiting for a while and trying to detect any leak that comes up. Okay. So this is the power on self test that Paul mentioned earlier. This is a very simple test that runs immediately when the system is powered on. It basically just goes through and checks that all the transducers are connected and powered on, setting some sort of value. This verifies the operation of our microcontroller, our analog to digital converters, and our pressure transducers. If these fail, then the entire system is non-functional, so it will hang, tell the user what happened, which sensor failed, and have them corrected before it proceeds. If all the sensors pass, then it will proceed onto the menu system where the user can choose what they'd like to do next. This is our much more comprehensive validation procedure, which is used to make sure that the entire system is functioning. Basically, as I mentioned before, it just goes through, gates off every section, pulls vacuum on them individually, holds it, makes sure they're not leaking, and then moves on to the next one. At the end of the procedure, it resets everything so it's ready for the actual operational tests, stores the passes and failures, alerts the user, and continues on to the menu. We ran into a couple of problems and challenges, which we tried to solve to the best of our ability. The first issue we had was that our pneumatic fittings required special tools to assemble, which we didn't originally have. We did talk to Lockheed about this, and they offered us the correct tools. However, we tried to do some of the assembly without those tools, which caused some damage. We ended up cross-threading a couple of components. We replaced those components, and were much more careful with the second set so that didn't happen again. We also had some issues with our electrical system, the first of which was our data direction register, which is a register on our microcontroller which sets the operation of certain pins. We had forgotten to set that, so our microcontroller was just sending and receiving gibberish. It wasn't able to communicate. Once we realized this and implemented the proper change, it worked as intended. The next electrical issue was with our relay driver chips. We had originally ordered the incorrect model, which meant they were set to operate at the wrong voltage, and again, didn't operate our relays. We fixed this by ordering the correct relay driver chips, and they functioned as intended. The final issue was a microcontroller failure. The microcontrollers are very complicated parts, and every once in a while, components fail. In our case, the entire C port failed, and we weren't able to send or receive data through that. That issue was solved by replacing the $10 chip. We also had some ordering issues. So at one point, the program administrator, who we placed all of our orders through, was on vacation. In order to stay on track with our project, we had to order some components on our own to keep up pace. We also had some issues where components either had very long lead times because they were coming from other countries, in which case we placed our orders as early as possible so that they'd get here in time. And then we had issues with suppliers sending us the incorrect components. So we placed the correct order, but they had sent the wrong part. That happened for both our vacuum pump and our pressure transducers, and the solution was to send back the incorrect part and wait for them to ship the correct part. And the last issue we had was that some vendors refused to talk to us because we're just students, we're not a large company with a corporate account, and the workaround was to find vendors who would.
So this is the final version of our pneumatic system. As you can, all the labeling here is consistent throughout all of our documentation. This is, right here is where a transducer used to be, but we found that we could eliminate it without causing any problems in the system. There we go.
As far as the final electronic design is concerned, you can see that we did still use the microcontroller system. Still the heart of our control system that controls all the actuation of our solenoid valves and the conversion of the pressure data. The pressure data comes from these pressure sensors here. It goes into an Adafruit ADS115 that communicates via an I2C bus. There's actually two of them that communicate via a shared bus with the microcontroller. That data is sent in a serial pattern over the I2C bus to that, and that's where we get the actual pressure data. From there, the microcontroller makes the decision that it needs to make, depending on what protocol that it's in. You can see over there on the right side of your screen that we have an overall code flow diagram. When the code begins, you start in the main procedure. The main procedure will automatically run the power on self-test. After the test is succeeded, it will go to a menu where you can either choose to rerun the power on self-test, you can choose to run the validation procedure, or you can choose to run the actual testing procedure. It is worth noting that if you try to run the testing procedure without first having validated the ports, that it will not allow you to test any of them because they are not valid for testing. They have not been validated, as it were, in their functionality, and therefore any tests you run on them would not be certified as functional. If you do run the testing procedure, it will bring you to a menu that allows you to select which UUTs you want to test. It will only allow you to select UUTs that have been validated. So if any specific UUT ports fail validation, but not all of them fail, then it will not let you test just those specific ports. If you choose one of those, it will bring you to a rejection menu and continue to ask you which ports you would like to choose. If you choose all the ports that you want, and you don't want to test all the ports, you can tell it that you're done testing, you're done selecting ports, and you can test just some of the 5 ports, which was a request by our client. After that, it will run the testing procedure, and it will tell you which ports have failed and which ones have passed the test.
As for some summary of our product right now, at the moment we have nearly completely finished assembly. One of the only remaining parts is the transducers, as mentioned before. We had the correct one selected but did not receive the correct transducers. They are currently on their way. We have the pneumatic system could not yet be validated without the transducers. That will be mentioned later in future works. An important step in this process was the documentation. So all the documentation had to be updated as engineers, leaving not just breadcrumbs, but a direct path to complete the assembly and calibration of the product. So we could not validate our pneumatic system 100%, but we were able to achieve communication between the test station and the computer. In future works, once the transducers have arrived and a temporary clamp is replaced with a permanent clamp for the pump, we can then wire the solenoids for the final assembly on our wiring diagrams. Once this is all done, the system can be calibrated. Once it's calibrated, it can be put on the line and be used by Lockheed Martin.
So for a few comments from our project sponsor, they said they were very pleased with our work so far and felt like this was a very good learning experience for our team. We would like to just say thank you to Lockheed for sponsoring our project. Any questions?